A supercritical fluid is any substance at a temperature and pressure above its critical point, where distinct liquid and gas phases do not exist. It can effuse through solids like a gas, and dissolve materials like a liquid. In addition, close to the critical point, small changes in pressure or temperature result in large changes in density, allowing many properties of a supercritical fluid to be fine-tuned. Supercritical fluids are suitable as a substitute for organic solvents in a range of industrial and laboratory processes. Carbon dioxide and water are the most commonly used supercritical fluids, being used for decaffeination and power generation, respectively. Properties. In general terms, supercritical fluids have properties between those of a gas and a liquid. In Table 1, the critical properties are shown for some components, which are commonly used as supercritical fluids. Table 2 shows density, diffusivity and viscosity for typical liquids, gases and supercritical fluids. In addition, there is no surface tension in a supercritical fluid, as there is no liquid-gas phase boundary. By changing the pressure and temperature of the fluid, the properties can be tuned to be more liquid or more gas-like. One of the most important properties is the solubility of material in the fluid. Solubility in a supercritical fluid tends to increase with density of the fluid. Since density increases with pressure, solubility tends to increase with pressure. The relationship with temperature is a little more complicated. At constant density, solubility will increase with temperature. However, close to the critical point, the density can drop sharply with a slight increase in temperature. Therefore, close to the critical temperature, solubility often drops with increasing temperature, then rises again. All supercritical fluids are completely miscible with each other, so for a mixture a single phase can be guaranteed if the critical point of the mixture is exceeded. The critical point of a binary mixture can be estimated as the arithmetic mean of the critical temperatures and pressures of the two components. Tc equals xTCA plus xTCB. For greater accuracy, the critical point can be calculated using equations of state, such as the Peng-Robinson, or group contribution methods. Other properties, such as density, can also be calculated using equations of state. Phase diagram. Figures 1 and 2 show projections of a phase diagram. In the pressure-temperature phase diagram, the boiling separates the gas and liquid region and ends in the critical point, where the liquid and gas phases disappear to become a single supercritical phase. This can be observed in the density-pressure phase diagram for carbon dioxide, as shown in Figure 2. At well below the critical temperature, e.g., 280 K, as the pressure increases, the gas compresses and eventually condenses into a much denser liquid, resulting in the discontinuity in the line. The system consists of two phases in equilibrium, a dense liquid and a low-density gas. As the critical temperature is approached, the density of the gas at equilibrium becomes higher, and that of the liquid lower. At the critical point, there is no difference in density, and the two phases become one fluid phase. Thus, above the critical temperature a gas cannot be liquefied by pressure. At slightly above the critical temperature, in the vicinity of the critical pressure, the line is almost vertical. A small increase in pressure causes a large increase in the density of the supercritical phase. Many other physical properties also show large gradients with pressure near the critical point, e.g., viscosity, the relative permittivity and the solvent strength, which are all closely related to the density. At higher temperatures, the fluid starts to behave like a gas, as can be seen in Figure 2. For carbon dioxide at 400 K, the density increases almost linearly with pressure. Many pressurized gases are actually supercritical fluids. For example, nitrogen has a critical point of 126.2 K and 3.4 megapascals. Therefore, nitrogen in a gas cylinder above this pressure is actually a supercritical fluid. These are more often known as permanent gases. At room temperature, they are well above their critical temperature, and therefore behave as a gas, similar to CO2 at 400 K above. However, they cannot be liquefied by pressure unless cooled below their critical temperature. Thermodynamics. In recent years, a significant effort has been devoted to investigation of various properties of supercritical fluids. This has been an exciting field with a long history since 1822, when Baron Charles Cagniard de la Tour discovered supercritical fluids while conducting experiments involving the discontinuities of the sound in a sealed cannon barrel filled with various fluids at high temperature. More recently, supercritical fluids have started to be deployed in several important applications, ranging from the extraction of floral fragrance from flowers to applications in food science such as creating decaffeinated coffee, functional food ingredients, pharmaceuticals, cosmetics, polymers, powders, bio and functional materials, nanosystems, natural products, biotechnology, fossil and biofuels, microelectronics, energy and environment. Much of the excitement and interest of the past decade is due to the enormous progress made in increasing the power of relevant experimental tools, the development of new experimental methods and improvement of existing ones continues to play an important role in this field, with recent research focusing on dynamic properties of fluids. Dima Bolmatov, V. Brajkin and K. Trachenko discovered that specific heat shows a crossover between two different dynamic regimes of the low-temperature rigid liquid and high-temperature non-rigid gas-like fluid. Rigid liquids are rigid like a solid on short time scales, but flow like a liquid on long time scales, while a supercritical gas-like fluid has the dynamic motions of a gas but is able to dissolve materials like a liquid. The crossover challenges the currently held belief that no difference can be made between a gas and a liquid above the critical point, and that the supercritical state is homogeneous in terms of physical properties. Bolmatov with colleagues formulated a theory of system thermodynamics and heat capacity above the crossover. In that theory, energy and heat capacity are governed by the minimal length of the longitudinal mode in the system only, and do not depend on system-specific structure and interactions. Dima Bolmatov with colleagues predicted relationship between supercritical exponents of heat capacity and viscosity and derived a power law for the supercritical state. The Fisher-Widom line allows to distinguish liquid-like and gas-like states within the supercritical fluid. Natural occurrence. Hydrothermal circulation. Hydrothermal circulation occurs within the Earth's crust wherever fluid becomes heated and begins to convect. These fluids are thought to reach supercritical conditions under a number of different settings, such as in the formation of porphyry copper deposits or high-temperature circulation of seawater in the seafloor. At mid-ocean ridges, this circulation is most evident by the appearance of hydrothermal vents known as black smokers. These are large chimneys of sulfide and sulfate minerals which vent fluids up to 400 degrees Celsius. The fluids appear like great black billowing clouds of smoke due to the precipitation of dissolved metals in the fluid. It is likely that at depth many of these vent sites reach supercritical conditions, but most cool sufficiently by the time they reach the seafloor to be subcritical. One particular vent site, Turtle Pits, has displayed a brief period of supercriticality at the vent site. A further site, BB, in the Cayman Trough, is thought to display sustained supercriticality at the vent orifice. Planetary atmospheres. The atmosphere of Venus is 96.5% carbon dioxide and 3.5% nitrogen. The surface pressure is 9.3 megapascals and the surface temperature is 735 K, above the critical points of both major constituents and making the surface atmosphere a supercritical fluid. The interior atmospheres of the Solar System's gas giant planets are composed mainly of hydrogen and helium at temperatures well above their critical points. The gaseous outer atmospheres of Jupiter and Saturn transition smoothly into the fluid interior, while the nature of the transition zones of Neptune and Uranus are unknown. Theoretical models of extrasolar planets 55 Cancri and Gliese 876d have posited an ocean of pressurized, supercritical fluid water with a sheet of solid high-pressure water ice at the bottom.